Today we're going to continue our discussion of electric fields, but we're going to look at it surrounding and inside conductors, and we're also going to look at the forces present due to electric fields. First up is the behavior of fields inside conductors. So the hard, fast rule about conductors is that anywhere inside the conductor, the electric field is zero, okay? So the reason why this is true is because, as we discussed way back when, all charge in a conductor lies on the surface, and that's because all of the charges are repelling, so they're trying to get as far away from each other as possible. So they spread out evenly on the surface. And there's this thing called Gauss's law, which basically says the electric field is proportional to the amount of charge enclosed by, it's called a Gaussian surface. It's kind of an imaginary construct that we use. But essentially it says if there's no charge enclosed in an area, so say we have a random area that we enclosed, if there's no charge in there, the field is zero. So anywhere right below the surface of a conductor, if we enclosed that area mentally, there would be no charge inside that enclosure, so the field inside that enclosure is zero. That's like Gauss's law in a nutshell. It's way more complicated than that, but tiny overview. So inside the conductor, the field is always zero. This leads to a pretty interesting consequence, which is that anything that's surrounded by a conductor is unaffected by external fields. And this isn't an obvious result because most people don't consider, if this is a conductor, the possibility that the conductor could have a hole or a void inside of it. So the little void I drew there, it would be like from a cross section. It would still have to be completely enclosed on all sides in 3 dimensions. But a result of Gauss's law would be that the electric field inside this conductor, even in the void, would be zero. So anything that is completely enclosed by a conductor is immune to external electric fields. And this knowledge led to the invention of the Faraday cage. So the Faraday cage is the enclosure surrounding an object. It's just a conductor enclosing an object to protect it from electric fields. So if you watch this video that I have a picture of here, you could see this guy messing around with electricity and Faraday cage and a little, I think, Benjamin Franklin figurine. I'll leave a link in the description below so that you can check it out. It's pretty cool. But this is also why if you get struck by lightning in your car, you're not going to experience any net electric field because you're surrounded by a conductor that is the car. However, that's only accurate if you're not touching the conducting part of the car, because you are a conductor and the charge will spread out evenly over a conductor. So if you make contact with the conducting car, then it's an issue. But anyways, go watch the video for electric fun. You can also look up YouTube videos of people in like Faraday suits, which is a conducting suit that you put on, and you can get struck by like Tesla coils or giant Van de Graaff generators, all sorts of stuff. People are crazy, but the science proves that being inside a Faraday cage or Faraday suit works. And then on the outside of conductors, right close to the surface, the electric field points perpendicular to the surface. So if you like drew little tangent lines here on the surface, I hope we all know what tangent lines are. If we drew tangent lines, they would be perpendicular, so at right angles. And that's because all the horizontal components, or I guess tangential components, are going to cancel out. Some math you can work out if you want to. It's a little tedious, not going to do it here, but they do cancel out and you just have a perpendicular component to the surface. Note that this still follows the convention where a positively charged surface will radiate a field that points away, and a negatively charged surface will radiate a field that points towards it. And once again, as I have stated, this is due to convention, okay? Forces follow the law of attraction and repulsion. Fields follow this convention. And that's really all there is to conductors that we're going to work on right now. If you want to know more about conductors, Gauss's law, fields and conductors, fields surrounding conductors, take AP Physics C. That would be awesome, because then I would get to teach another AP class and not have to deal with freshmen. But I digress. All right, we're going to move on to forces inside fields. The title of this section of the book is Forces and Torques in Electric Fields. I'm not going to talk about torques because it's not in the scope of AP Physics 2, but torques can exist in electric fields because forces can exist in electric fields. If you want to know more about it, email me, ask me, or read the book. So finding force from electric field is super easy, and that's because the definition of electric field, if you remember from last time, is the force to charge ratio. So algebraically solving for force here is super easy. You can get force equals the electric field times Q. Easy peasy. The only slightly tricky thing here is about the direction of the vectors. So as I have mentioned in the previous video and earlier in this video, the convention for fields is that they radiate away from positive charges and towards negative charges. That is convention, and it's because we assume a positive test charge. However, we determine forces due to point charges or anything else by attraction and repulsion. So when dealing with forces and fields at the same time in an equation like this, it's easy to get confused which direction something should be pointing. And the rule for figuring it out is this. If Q, the charge you're looking at the force on, is positive, the force on that charge is in the direction of the field. So you look at the field, or you think about the field, or you have drawn the field, and you know which direction the field is pointing because you're finding force from the field. The field must be known. And if the charge you're observing is positive, it follows the direction of the field. And if it's negative, it follows the opposite direction of the field. It goes backwards. And even if you don't remember this rule specifically, it's pretty easy to figure out when you're just thinking about things, because you would know that a positive charge would be pushed away from a positive point charge and pulled towards a negative one, or a negative charge would be pulled towards a positive and pushed away from a negative. So really you can just look at the diagram, think about the situation, and figure out from what you know of charges which direction the force should be in. And a note about problem solving on finding these forces: a lot of times when we find the net force on an object, we look for the sum of all the forces. Here, if you've got multiple point charges, so say you've got a distribution, we'll make it a quadrupole because I like quadrupoles as a particle accelerator physicist. We could find the electric field for each one of these particles, find the force on Q due to that electric field, and have 4 forces, add those up with vectors. Or we could find the field for each one, add together all the fields, and then find the force from the final field. Either one of those things is mathematically equivalent and is fine to do. But typically what I would do is find the field, say we'll be looking at a charge that is right here. I would find the field at that point and then use this equation to find the force. So before we go, of course, we have to look at an example. This one is about a cathode ray tube. So cathode ray tubes are basically things that shoot electrons which ping on something else and are observed and make televisions and monitors and such way back in the 90s. So that's just the example we have. And a CRT designer from way back when has specified that the electrons must leave the 4 centimeter wide electron gun with a speed of 6 times 10 to the 7th meters per second. What electric field strength is needed inside the electron gun capacitor? So here's what a cathode ray tube electron gun looks like. Okay, we've got positive end, and it's got 2 plates. There is a small gap in the plates on the right because that's where the electron gets shot out of. So first we're going to figure out which side is positively charged and which side is negatively charged. So we're looking at electrons. Electrons are negatively charged. That means they go against or backwards from the typical field lines. So if we need the electron to be moving to the right, that means the field lines have to be moving to the left. So the electric field looks like this. And for the electric field to look like that, this side has to be positively charged, and the other side has to be negatively charged. And this makes sense because electrons would get attracted to the positive side and repulsed from the negative side. And we know that this gap is 4 centimeters, which is 0.04 meters. So the question is asking what electric field strength is needed inside the electron gun capacitor. And the information we're given is the distance for the acceleration and the speed it has to leave from. And it does start with a 0 speed. I forgot to put that in the question, but it does. So we got an electron. It's going from 0 to 6.0 times 10 to the 7th meters per second over a distance of 0.04 meters. Sounds like some fun kinematics to me. From this, we will calculate the acceleration, then we'll use the acceleration and the mass of an electron to determine the force necessary. From the force necessary, we can find the electric field strength. So the kinematics equation that we can use here is velocity final squared equals velocity initial squared plus 2a delta x. Plugging everything in here, we have a velocity final of 6.0 times 10 to the 7th. So 6.0 times 10 to the 7th meters per second. That's squared equals velocity initial, which was 0, times 2a, and delta x is 0.04 meters. So we'll just algebra that out. You get a equals 6.07 times 10 to the 7th meters per second squared over 0.08 meters. Use a handy dandy calculator on that sucker and you'll get a giant acceleration of 4.606 times 10 to the 16th meters per second squared. Quite the acceleration. All right, and from this acceleration we can calculate the force. So we know force necessary equals the mass, so we need the mass of an electron. The mass of an electron is 9.109 times 10 to the negative 31st kilograms times that acceleration 4.606 times 10 to the 16th meters per second squared. Type that into a calculator and you'll get a necessary force of 4.195 times 10 to the negative 14th newtons. So that's how much force is needed to accelerate the electron from 0 to 6 times 10 to the 7th meters per second in the space of 4 centimeters. Now all we need to know is what the electric field strength necessary to cause that force is. So we start with our equation, force equals field times Q. And our Q here is the charge of the electron. So we've got force of 4.195 times 10 to the negative 14th newtons equals the field, which is what we're looking for, times Q. Q for an electron is 1.60 times 10 to the negative 19th coulombs. And all you got to do is divide. And when you divide that out, you get an electric field of 2.622 newtons over coulombs. And there you have it. It's not too bad. It's just basically working backwards from what we were doing the other day.